Yeah, I'm ready. Thank you, Miko, for the introduction. Thank you, the Sean and the Newton Institute for the invitation. So this work has the purpose of determining the topology of metric of space-time with a radar-like device. Of course, this is the ultimate goal, but this is far from being able to realize this at the moment. So this is a wormhole that has not, on the left, a gravitational wormhole. It's a shortcut in space-time. It has not been found in the universe yet. On the right, you have a picture of an electromagnetic wormhole. Those have been, at least theoretically, done, and some practical magnetic monopoles have been found in the laboratory. Okay, so the second part of the talk is about applying this to nonlinear equations and using the fact that nonlinearity, I don't know why the movie is not working. Let me see, 1 second. There it is. So we use the interaction of waves. The equation is nonlinear, there is interaction of waves. Here they have 4 waves coming in, and then intersect at a point, and a new singularity is generated that will determine the structure of space-time. So in fact, if A is non-zero in this nonlinear equation, then there is this interaction, and you'll be able to, for the wave to come back to the region of observation and be able to recover the coefficients A and C in some cases. So as I said earlier, the question is, can you recover the structure of space-time when you see light? Light is maybe from billions of years ago, coming from many point sources varying in time. We can also observe gravitational waves now since 2015. The problem with this was light that doesn't come straight. There is gravitational lensing. If there is a very large mass, then light is deflected. And so that complicates the observations. Of course, for instance, we can see on the right the picture of Einstein's cross, where you have 4 images of the same star. So there are 4 geodesics, or 4 that come together at some point. And this is another phenomenon called the double Einstein ring, another case of gravitational lensing. This happens when the star that you want to observe, there is a large star in the middle, and the observer are all aligned. And then light doesn't know where to go and goes all around. So that's why you see the double Einstein ring. This is very similar. The explanation actually is the same as what's happening in optics, in something called conical refraction. When you shoot a ray of light in the direction of an optic axis of a biaxial crystal, splits into a cone, and you see 2 rings of light separated by a darker ring. The double Einstein ring was actually predicted by Einstein himself. And that has been observed. And then since 2015, as I mentioned earlier, we can observe now gravitational
leading to their ultimate collision and merger to form a single black hole.
Gravitational waves.
The power of the gravitational waves was 50 times greater than that of all the stars in the
Yeah, so two black holes collide and generated a huge gravitational wave that was observed for the first time in 2015. Of course, this observation won the Nobel Prize in Physics. So to formulate the problem more precisely, we have a region of space-time here on the right. It has some points here, and the regional observation is on blue. Of course, this is we cannot draw it in four-dimensional space-time. So you have a point source here. It generates waves. These are the fronts of the waves. And then you observe the intersection of the fronts with the regional observation, and this is for every point. And the question then is, can you recover the structure of the region on the right from these observations? We make the observations in the region in blue. So we intersect the light cones, the cones of light coming from the points here with the regional observation. And we want to recover the structure of this region here. Okay, so to formulate precisely the problem, I don't know, it's very, we take in a space-time, we're usually going to take n equal to 3, so 1 time and 3 space dimension, but in general, you have the Minkowski metric. Actually, this is the first solution of the vacuum-Einstein's equation, minus dt squared plus dx squared. So signature is minus plus, etc. And the null vectors are the ones for which the metric vanishes, so indicated in red here. And we're going to, and we denote the cone, the future light cone starting at this point by point Q, by LQ plus or minus, the backward light cone and the forward light cone. It's very different from Riemannian geometry, where, of course, G is positive definite matrix. So we have an n plus 1 dimensional manifold will be Lorentzian manifold. For the people who are not familiar, you just can think of Minkowski metric, and there is a time orientation. So that means the tangent space at the point Q is like Minkowski space. Then you take the null geodesic, which is the propagation of light. These are the photons propagate along geodesics of the metric, and this is exponential map starting at the point Q. Those are the null geodesics. It's null because the metric vanishes on the light cone. Again, the future light cone is defined where this is new, is in the future, and we have similar one for the past. It's a lot of definitions, but I hope it's not going to be. Just think of the Minkowski metric for the people who are not familiar. So again, LQ plus is a set of future past pointing light-like vectors. The causal vectors are called the ones that are time-like and light-like. So they are in the cone, outside, and they are inside. So this is the propagation, and the world line of an observer is inside the light cone. And a curve is time-like, light-like, causally the tangent vectors are time-like, light-like, causal. That's just some definitions. So light-like is, again, is the metric vanishes. Space-like, if the metric is positive, it's like a space. And time-like if the metric is negative. So this is the future. We go into the future of the light cone and the past of the light cone. So a time-like geodesic corresponds to the world line of an observer, as I was mentioning before. And then you have two points PQ joined by this time-like geodesic. So this notation P mass less than Q means that can be joined by future point-in time-like curves, and P less than Q means can be joined by future pointing causal curves. Causal means the ones inside the light cone and also in the boundary outside the light cone. Then you have the chronological future, for instance, of the point P is indicated here by I plus, and the causal future is including the inside, is J plus, and then you have the intersection of the backward light cone and the future light cone denoted by IPQ or JPQ. You include the inside as well. And then I think this is the last definition. A Lorentzian manifold is globally hyperbolic if there are no closed causal path in the manifold. That means geodesics don't close, so you can go to the future, but you cannot come back. And this set is compact. JPQ is compact, indicated here. The importance from the analysis point of view is that if the manifold is globally hyperbolic, which is a reasonable assumption, then it behaves very much like a Minkowski metric. This is beta psi is positive, it minus dt squared plus a Riemannian metric, a positive definite symmetric matrix for every t. And we're going to use a notation x is ty. Y are going to be the space coordinates and also going to be denoted x0 for the time and x1, x2, x3 for the spatial coordinates. Okay, so I hope not too much notation, but this is now the setup of the problem. So we want to find the structure of space-time for W. What is the metric in W? What is the topology and the differential structure? So we send light, the fronts of light from points in W, like I indicated before. So you take the point Q in W and you take the light cone. That's where light propagates. Light propagates on the light cone, and you intersect that with the region of observation, which in this case is called V. So this P plus and P minus are the points in the world line of an observer like us, and this is the neighborhood of it. So you intersect the light cone with the region of observation. So these are this is the light observation set. And you do this for every point Q in W. This can be very far in the past, billions of years away. The earliest observation set, because the geodesics or the light can have many complicated behavior. If there is gravitational lensing or things of that sort, they can come back and so on. We look at the earliest light observation set. And interestingly enough, in the physical literature, the light observation sets are called line cone cuts, and they were defined for different purposes. And I learned about this when I gave a talk at Santa Barbara about this, and Horowitz is a physicist in the university, and after my talk, he mentioned this. But the theorem in this case is you take an open, smooth, globally hyperbolic Lorentzian manifold, a dimension bigger or equal than 3. And you take 2 points that are joined by time-like geodesic. You take a neighborhood of this world line of an observer and W in a relatively compact set. So this is the set that we want to find the structure. Assume that we know these cuts or this light observation set, the earliest light observation set. Then we can recover the topological structure, the differential structure, and the conformal structure of W up to diffeomorphism. Of course, this is invariant on the diffeomorphism. It's only, you can at best recover the conformal class, because if you recall, the light cone is where the metric vanishes. So the metric vanishes in the light cone. So you take a multiple of the metric, it still will vanish. So that doesn't change. So the light cones are the same for a metric and a multiple of it, the conformal multiple of it. Therefore, at best, you can recover the conformal structure of the metric W up to diffeomorphism. So I'm not going to explain the proof. But there is a question of how can you recover the conformal factors? So you can recover the metric up to conformal factor just geometrically. We're going to see later that if you have some equations, you're able to recover the conformal factor by computing symbols and things of that sort. But just geometrically, so we need a particle that is slow enough and fast enough. So the v is very close to the speed of light, for instance, but it's not the speed of light, because we need a cone that is not invariant on the conformal factor, and don't interact much with electromagnetic fields, can be detected as producing sufficient quantities around the universe. And this is the neutrino. The neutrinos are tiny but non-zero mass and are typically relativistic, and they are electrically neutral and interact very weakly but can be observed with specialized detectors. They are produced in great numbers in supernova explosions. There is a lot of data from neutrinos. About 99% of supernova energy is carried by neutrinos. So what is a supernova? Is exploding death of a big star. A supernova releases both photons and neutrinos in great numbers, and the neutrinos are a bit slower, but not, it's very close to the speed of light. It's 10 to the minus 20 factor, but release a little bit earlier, so the catch-up time is often long. And we are going to treat neutrinos as small perturbations of photons and relativistic Jacobi fields. And the neutrino cone depends on the motion of the dying star, and the light cone does not. And the theorem is that we know already the conformal class of the metric. We want to recover the conformal factor. The measurements of neutrino cones in an open subset of the space-time determine the conformal factor in the light path to the measurement sets. So the conclusion from these two theorems is that photons and neutrinos together determine the full geometry of the visible part of the space-time. So before we had the theorem that these are the light cones produced by light, photons, and in this case, we added another information to recover the conformal factor, which are the neutrinos. So photons and neutrinos together determine everything. So this is a cartoon. This is the world line of a star. It's a supernova, the explosion. You have the light cone, and inside, very close to it, is a neutrino cone. So we know the intersection of these cones with the region of observation, you can recover the full metric. Of course, these are idealized problems. In practice, we don't know all the intersections and so on, but hopefully this will give a method to get an approximation. So what we measure is not deviation of light rays, but deviation of light cones. We need to take the components of the ultra-relativistic Jacobi fields normal to the light cone. It's not a difficult inverse problem. In fact, But the important is observation that the neutrinos are the right thing to determine the conformal class. If gamma is the light ray, the direction normal to the light cone is tangential and normal to the light cone. And the normal component of the Jacobi field is given here, and the Jacobi equation is very simple in the tangential component. The second derivative is 0. So the problem, inverse problem, is quite simple. So, but this is a little bit more technical. The important thing is that these two cones intersected with the region of observation determine fully the Lorentzian metric and the topology and the differential structure as we did, as we mentioned before, of the region that W that we wanted to determine. For boundary value problems, for relativity, this maybe this is not so important, but for many equations, nonlinear equations where you have boundary values, and I'm going to give several examples of this, it's important to look at what is the boundary light observation set. So suppose you have a set S in the interior of a manifold with boundary now, and use the region of observation on the boundary, and we intersect the data, we take the cone, and then we're going to take the reflections of this is the same as before. We had to take the light cones, intersected with the region of observation, which is U at the boundary now, and we're going to also take reflections from this. And there will be the theorem, I will state it more precisely, to determine the topological differential and conformal structure of this set S inside. So we need to consider also reflections. You take a geodesic, you take vector V at the boundary, reflects using a Snell's law. The angle of incidence is equal to the angle of reflection. So the continuation of this geodesic is as a broken null geodesic. So it breaks down and reflects and so on along the boundary. So it goes, geodesic goes here, 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 and so on. But you only look at this in the set of observation U. Okay, so there are some geometric conditions that one needs for stating the theorem. The first is what's called null convexity. It means that the metric, well, this is more technical, but essentially think about convexity of the manifold. So there are, the point is that all the null geodesics that start in the interior intersect the boundary transversally. That's what this condition guarantees. So we define the light cones now using the broken geodesic. So again, I repeat, you take the cone here, starting at the point Q, on the region that you want to determine. You consider the reflections, and you intersect it with the region of observation N on the boundary. So again, the setup is the Lorentzian manifold with strictly null convex boundary, again, so that the geodesic starting in the inside intersect the boundary transversally. There is a time. You take a set of sources in the interior and you observe on the boundary. And there is an assumption which is necessary. I'm going to give an example why we need this condition. You take the forward light cone, which includes the broken light cone intersected with U, is not the same with the other one if the points are different in S. This is the region where you want to recover S. I think it's indicated here. Yes. And the theorem that I proved with Peter Hintz is that you know U, that's the boundary, and this intersection of these broken cones with U determine uniquely the set S and the conformal class of the metrically, topologically, differentially, and conformally. So again, you can determine the topology, the differential structure, and the conformal multiple of the metric from this observation. So this will be useful for boundary value problems. Yeah. So the point is for nonlinear equations, the reason to define this, the light observation set, for instance, is that in the movie that I showed at the very beginning, you will be able to recover that here because of the interaction of waves. So this intersects at the point Q, and that generates a new wave. And this wave is the one that is observed in the regional observation. You can recover the light observation set. That's the point. And for boundary value problems, we have something similar. Of course, then the information is at the boundary, the reflection is at the boundary, the wave is at the boundary. Okay, so this is and it's an example of strict convexity. Suppose you have what's called a stationary metric, which is the minus dt squared plus a metric, Riemannian metric H, is independent of T. So you have like a cylinder. And the strict null convexity of the boundary is the same as strict convexity of the boundary of X. So this is X, the cylinder cross R in time. You take minus dt squared plus H, and then, so that's a natural condition of convexity. And this assumption that the light cones, which remember in this case includes the reflections, have to be different because otherwise we cannot determine it uniquely. You can have the same in the set U on the boundary. You can have for the set S1 and S1 union S2, you take the light cone starting from here and from here, because it reflects the light cone here, passes through here, and it generates exactly the same light cones. That includes the broken light cones. So S1 and S1 union S2 are indistinguishable in this neighborhood if you have the data here in U. Of course, you take other data, then they will be distinguished. But in the set U, they're indistinguishable. So that's why we make this assumption that these light cones are different for different points. Okay, so these is applied to nonlinear equations. And a simple example is a 2 + 1 dimensional manifold. So you have two space dimensions and the time. This is the wave equation associated to the Lorentzian metric, and you have a cubic nonlinearity and a source here, and A is non-zero. So the nonlinearity is always present. Okay, so using, this is what we started with Kurilev and Matilasas in 2018, and was published in 2018, was in the archive 4 years earlier. I mentioned this example because it's a simple nonlinearity. It's exactly UQ in a three-dimensional Lorentzian manifold. You take three sources, epsilon 1, epsilon 2, epsilon 3. One looks at multiple linearization. So these interactions of, in this case, we'll look at interaction of three waves. We take three sources here. So we generate these sources in the region of observation, and UI is simply the inverse of the FIs of this. And these are conormal distributions. For example, F1 is T minus X1. This goes in the direction X1. This is T minus X1 to the, it's very smooth. It's not completely smooth, but it's C9 or something like this. This is T minus X1 if this is positive, and 0 if this is negative. So you're taking a progressive wave coming in, and similar for F2 and F3. And then you can show that U is the sum of the UIs, and then there is a factor epsilon1, epsilon2, epsilon3 here. There's the inverse of the triple product, and that generates a new wave. This interaction of the three waves here generates a new wave. So this is the picture. So you have U1, U2, U3. Q, these are the plane waves coming in, and they intersect at the point, at this point Q here, is the intersection of the singular support of these three waves. Remember, these are progressive waves. The singularities are just on the waves. For instance, this is a wave going in the direction x1. T is equal to x1, and T is moving. And then the singularities of the triple interaction, and now you look at the triple interaction of the waves, the singularities of these. So you have to multiply these distributions, which are quite smooth. I mean, you can multiply them. It's not C infinity, but they are C9 or something like this. You can analyze the singularities of this in terms of wavefront set for the people who are familiar, or the singular support. And then you're going to find a new wave, which is indicated here, which gives the light observation set. So the singularities of this, you take the triple linearization, gives the light observation set. It gives exactly this. And this you observe in the region of that you have. So this is the idea that applies to many type of equations. This, of course, is a simple example, but the idea for many equations is the same. For instance, we apply this with Peter Hinz and Shai for this equation, and we consider the Dirichlet to Neumann map. So this is where Dirichlet data is given, and this is U, and this is where Neumann data is given. And one particular interesting case where the Dirichlet data is in the same as the Neumann data. And the propagation of singularities is very well known for the under the strict null convexity assumption, how singularities propagate. Is the geodesic flow, the broken geodesic flow, which is due to Taylor and Merlo-Shostra and so on. Okay. So this is exactly the method that we apply. We can, the same idea that I mentioned here for the cubic case, applies here for the Dirichlet to Neumann map using the boundary light observation set. So you can recover the boundary light observation set in this case, and therefore the conformal class of the metric G. The original example that we studied many years ago was Einstein's equation. The Einstein tensor is equal to the stress energy tensor. This is the geometric part. This is the mass or the force part. And the Einstein equation is given in terms of the Ricci tensor and so on. But in wave map coordinates, the Einstein's equation is a quasi-linear hyperbolic equation having a conservation law. And then we're going to add sources and couple Einstein's equation with matter fields given by this equation, the Klein-Gordon equation. These are force. So we need to modify the stress energy tensor with a force here, and the metric for t less than 0 is given g hat and phi is phi hat. Okay, but the stress energy tensor, the F1 and so on needs to, and the F2 need to be chosen so that you have these are the Bianchi identities, the divergence of these tensors is equal to 0. This is a conservation law. It's a conservation of energy in the universe. And the theorem in this case that we prove with Lauri, Oksana, and Mati, and Kurilev, and then and we have a generalization with Wang. In the first result, the conformal class of the metric is determined with Iran Wang. We prove that you can actually recover the conformal factor itself. So suppose you know everything about the metric G in this region of observation. This is again the time lag, the word line of an observer, a time lag geodesic. You know the metric there, you know the matter field there, you know the source head there. These are the sources. The sources here. It consists of this pair, and so that the divergence equation is satisfied. This data set determines uniquely the metric on this cone, which is the causal cone. So these are the cones so that the waves that you send starting in this time lag geodesic and the word line of observer come back. That's the maximal diamond set, the causal set, where you can find the metric. So then you can recover the metric in this diamond set. So this is, of course, very complicated, but there are much simpler examples. And this is similar to what we had before, which is this now is fourth space dimension, and the singularity is u to the 4. But you have a manifold with time-like boundary. So you have u equal to f on the boundary and u 0 for t less than 0. So this is the boundary value problem. The inverse problem, you can recover the metric G and the coefficient A from the Dirichlet-Neumann map. And the theorem that we prove with Peter Hintz is, in this case, it has the same boundary, and the Dirichlet-Neumann map acts on sufficiently regular functions are equal. Then there exists a diffeomorphism. So how I'm doing with time, I don't. Then in this case, of course, you cannot recover, everything is up to diffeomorphism, but this identity in the region of observation. And this is a conformal factor, so that beta is equal to 0 on the normal derivative on the boundary or in the region of observation. And then one metric is a conformal multiple of the other, and the coefficients also are conformal to each other. But we know something about this conformal factor, that the wave equation applied to e to the minus beta is equal to 0. So in this case, that in some cases you might be able to show that beta is identically 0, because we have the beta and the normal derivative are 0. Of course, we don't have the unique continuation theorem of Tataro to guarantee that this must be, the beta must be 0. But in some cases, it might be possible. But see, this is what you can recover. So we know something about the conformal factor in this case. And there is, since I'm running out of time, let me just say, you can do similar things for quadratic nonlinearities. When you have the wave equation, so you have the terms involving the gradient. It's a quadratic form in here. And this is a simplified model of the wave maps, but that's a system. In this case, we just have a scalar equation. So I'm going to jump over this. And another physically interesting example, besides Einstein's equation, is the case of nonlinear acoustics. And it has been observed when you have a high-intensity ultrasound, there is a nonlinear interaction. The waves at frequency, a certain frequency generates frequency at the double of it. So you have FC and 2FC here, the pulse after propagation. And the one model for this is the Westerveld type equation, which is a quasi-linear equation. It's actually simpler in some sense and more complicated in others. It has the sound speed. This is the sound speed. And this is the coefficient of the nonlinearity. So you have dt squared of p squared here equal to the Laplacian p. You have minus Laplacian p. This is the standard acoustic wave equation. You have a boundary data, and p initially is 0. P is the initial velocity, the position and initial velocity are 0 and t equal to 0. And beta is a nonlinear parameter. And we want to recover this parameter beta from the Dirichlet to Neumann map. Let me mention that the sound speed, there are some results that you can recover the sound speed under, for instance, the simplicity condition or the foliation condition. If you look just at the linearization of this equation, but I'm interested in this case in the recovery of the coefficient of the nonlinearity. And you do second order linearization in this case that also always depends on the equation, what type of multiple linearization. Sometimes you have to do all the linearizations. I will point out one example, because here you have a quadratic nonlinearity. So you look at second order linearization. So you take the Dirichlet to Neumann map, epsilon 1, epsilon 2, epsilon 2, F2, and you get an equation involving the beta and derivatives of products of solutions, and then U0, where U0 is the solution of the backward wave equation. This is typical, so this is like the back propagation. So we look at particular solutions of but this is for the linear equation. Okay, and these are, you see the solution of the linear equation, backward wave equation, satisfying these conditions. So you send the wave back, then interacts with these waves here, and then you're trying to recover the coefficient F, beta. This can be done using plane waves like we had before, but there is another method that has also been applied, especially to recover coefficients of nonlinearities, like in this case, which is Gaussian beam solutions. I mean, you can construct solutions of this equation concentrated in geodesics. Geodesics as the propagation of the rays, the normals to the wave fronts. So the rays or the by characteristics. So you take U0, U1, U2 Gaussian beam solutions joining points on the boundary, and you plug them into this identity, and then you recover a weighted rate transform of this function beta, and you can invert it using methods that have been developed by Gabriel and Miko, and also Faiz Hamadi and Oksana have something similar. So this you plug them into this equation. You see, these are concentrated near geodesics. So you're going to get some information about integration of beta along these geodesics, but with some weight. So there are some numerical experiments that were done by Sebastian Acosta for the standard Shep-Logan phantom, depending on the length, the size of the image, and lambda is the wavelength. And you can see here the picture gets better as this gets larger. This is the standard model, the benchmark that's used for medical imaging, the Shep-Logan phantom, the Shep-Logan phantom. This is another case. Okay. There is a more general model for nonlinear acoustics. This was pointed out by Kaltenbacher and Randell. This is F is more general function, not like the Westerveld equation that involves just the derivative of p squared. So it's more general. You can consider also that case. And in this case, you have to do multiple linearization. And we assume that the F has a power series expansion into these coefficients here, dt squared of the p to the n plus 1. And these are a smooth function. And the inverse problem is, can you recover these coefficients? So we're assuming it's analytic in these variables from the Dirichlet-Neumann map. And the answer is yes. But in this case, you have to do multiple linearization. And this is theorem with Yang Shan. There is an M so that it is nonlinear. The Dirichlet-Neumann map determines the nonlinearity. And when we look here in the nonlinear interaction of 4 distorted plane waves, like I showed at the very beginning, you have 4 waves interacting. You recover beta 2, beta 3, beta 4 from the first order linearization. And then the other coefficients, the larger coefficients, beta n for n bigger or equal than 5 from nth order linearization using an inductive procedure, type of the uninductive procedure. There has been many works. I'm not going to be exhaustive, and I'm sorry if I didn't mention your work here, but many works on this type of problems, Einstein's equation I already mentioned, nonlinear elasticity, Yang-Mills equations, the inverse scattering for the critical nonlinear wave equation, semilinear equation, many works. Other works for the Westerveld equation was done by Eptaminitakis Stefanov. And let me finish with that. Thank you. Okay, sure. How do I do that? I had to get stop sharing. Here it is, stop sharing. Okay, I stop. I cannot hear. Yeah, now I can hear you. Yeah. Yes, yes. 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 Actually, I'm looking into some of them, but let me tell you one problem. So suppose you take a Maxwell anisotropic Maxwell equations. In this case, you would like to recover so you take the coefficient mu, the magnetic permeability to be 1, which is standard for most materials. So it's a crystal. Then the question is whether you can recover the epsilon, the matrix, epsilon, the electric permittivity from the Dirichlet-Neumann map, for example, or the scattering. And the idea is to use this extra wave that you have, because there is this propagation along, very similar to what's happening for the nonlinear equations. There is a propagation. There is a cone of propagation that comes out in the direction of the optic axis of the crystals. So one would like to use that because it gives new information. No. This is something we're working on. I don't know any application at the moment. We have a paper from. I have a couple of papers on conical refraction where you construct solutions to the equation. Sorry? Okay, sure. Yes, it's a good question. Try. One can prove the following, that from the Dirichlet-Neumann map from the Lorentzian wave equation, right? We're talking about metrics depending on time now, right? Then that you can recover the light observation set by following the geodesics, the propagation of singularities. However, the theorem with hints require that you have to map diffeomorphically these light observation sets to each other, and that's the problem. So I don't know how to. In other words, you need to know you have the intersection of the light observation set with the boundary. You want to know where it comes from in the interior, and that's hard to determine. So I think there should be. This is very similar to for the Riemannian case of the scattering relation. It's in some sense the analog. So I'm trying to avoid using Tataru's unique continuation theorem, which is not true for the metrics depending on time. And so the light observation set might be on the boundary light observation set in particular. The boundary light observation set more than the light observation set should be helpful, but I don't know exactly how.